The Grand Canyon, a colossal labyrinth of towering buttes and deep-sided canyons. For over a century, scientists have puzzled over how one small river could cut such a deep slice through the earth. The Grand Canyon formed through processes deep within the earth, invisible to the eye. Today, new discoveries point toward new answers. Scientists are on the brink of understanding the geological forces that created one of the natural wonders of the world, the Grand Canyon. It's a landmark so immense that you can see it from space. 277 miles long, up to 18 miles wide, and 1 mile deep. The Grand Canyon is one of the deepest chasms on Earth. Its walls plunge sheer into the Earth's crust. The Colorado River sliced through 2 billion years of our planet's history in less than 5 million years, exposing layer after layer of geological time. The first humans walked here thousands of years ago. Since then, the canyon has inspired awe. How did it come to be here, and what secrets lie hidden in its walls? To many Native Americans, this land is sacred. They have revered the canyon for centuries.
The canyon is a very spiritual and powerful place. Our legends say that we actually came from the bottom of the canyon.
Scientists like senior geologist John Spencer consider the canyon a treasure and a mystery.
It's a bit startling because all around it is very flat. You can be 100 feet from the edge of the canyon and think this is a rather boring landscape, and then you walk over and look into the canyon and all of a sudden there's this monster canyon in front of you.
The layers of rock in the canyon walls formed over thousands of millions of years. The deeper you go, the further back in time you travel. At the top, the newest rocks. At the bottom, the oldest. The Grand Canyon appears to be upside down. On top, fossils from an ancient sea. At the bottom, remains of an old mountain range. Carl Karlstrom, geology professor at the University of New Mexico, is an expert on the oldest rocks of the canyon, 1 mile down. They reveal what the southwestern U.S. looked like 2 billion years ago.
We were interested in what's the oldest chapter of Grand Canyon history, and these rocks are so spectacularly exposed that we have the opportunity to study the earliest history in Grand Canyon.
What's strange about these rocks at the bottom is that they are part of an ancient mountain range, now buried under thousands of feet of rock. They are the remains of a range called the Vishnu Schist, a layer of metamorphosed rock that dates from around 1.7 billion years ago. The human eye sees a line of rock. Karlstrom's instruments see evidence of a mountain range that once towered 6 miles above. His techniques bring the past back to life. His clue is the minerals in the rock that change chemical composition under pressure. More rock on top means more pressure on the rock below. That forces a mineral in the rock, garnet, to take up more calcium. The higher the calcium concentration within the garnet, the brighter it looks under a microscope. This tells scientists how deep a rock was buried.
We've learned that these rocks were buried to great depth, and the amount of pressure that they experienced was equivalent to about 6 miles of rock above them.
Karlstrom's findings have helped other geologists visualize how this area may have looked 1.7 billion years ago. Ron Blakey is a professor of geology at Northern Arizona University in Flagstaff. He studies ancient continents and discovered that California wasn't always America's west coast.
It's very likely that the coastline of North America at this period of time was just south of Wyoming, perhaps along the Wyoming-Colorado border, and it extended up into the Lake Superior region and then up into Canada. So I would say that perhaps only half to two-thirds of North America had been built at that period of time.
The Vishnu Mountains stretched across a very different landscape. The south of North America did not exist as we know it today. The mountains towered up out of an ocean along the ancient coast. They eventually became part of the North American continent and formed the basement rocks of the Grand Canyon.
I imagine it looked like a bit of a train wreck where each of these island chains was perched offshore, a series of island chains that had substantial mountains but fairly high peaks, like in the Aleutians.
6 miles beneath the summits of these mountainous islands, the rocks were developing that distinctive calcium signature. The mountains above didn't last long. In around 500 million years, erosion ground them down until all that was left was this at the bottom, the Grand Canyon's most ancient layer. As we rise up the side of the canyon, we travel forward in time. Each foot takes us closer to the present day, and each period has its own history. Over hundreds of millions of years, the land masses continually change shape. Forces deep inside the Earth cause continents to break apart, drift away, and form new ones. Deep trenches open up beneath the ocean. Sea levels change and flood low-lying areas. At least 8 separate seas have flooded this area since erosion cut down the Vishnu Mountains. They covered the land, stayed for a few million years, and retreated again. The evidence is here, nearly 2,500 feet above the modern Colorado River and 5,500 feet above present-day sea level. These are the remains of oyster beds that flourished here nearly 100 million years ago. The Cretaceous Sea stretched from Kansas in the east to Nevada in the west, from Mexico in the south to the Arctic in the north. It was a shallow seaway that covered much of the continent. Sea creatures sank to the bottom of the ocean and fossilized in a thick gray layer of mud. Scientists call it the tropic shale. Wayne Ranney is fascinated by this region, rich in fossils. It gives him a clear idea of this area's history.
This oyster bed, which contains millions of oysters, was from a sea that was a shallow sea that covered the interior of North America between about 80 and 90 million years ago.
Oysters weren't the only creatures living in this ancient sea. Life was abundant. Sharks, turtles, and ammonites also inhabited the waters. Today, as erosion slowly wears away the layers of rock, new fossils appear. And in 2005, just 70 miles away from the edge of the canyon, paleontologists found the well-preserved skeleton of a plesiosaur, a dinosaur-like fish-eating reptile. It lived around 90 million years ago. Clear proof that this area was under the sea at that time. The seas left deposits of mud, sand, and the remains of living creatures. Sea currents moved this material, which then settled. And over time, the deposits turned into layers of sedimentary rock. Ron Blakey explains.
What I'm going to show you now is a form of sedimentation. I have here a glass cylinder that's filled with water and sediment, mostly sand. And what I'm going to do is shake this up. And the shaking up provides energy that allows the sand grains to move around this cylinder of water. And then when I set it down, that energy is removed and the grains will immediately settle out. Let's see what happens. As you can see, the coarsest grains have already settled out, and finer grains are settling. And now most of the sand is out. The water is still cloudy because there's some fine material still in suspension within this cylinder. But all the energy of the system has been removed, and so now even the finest grains over time will settle out to form a layer of sediment.
This process demonstrates how sedimentary layers built the Grand Canyon. Over the course of time, the glass cylinder turned many times. And when the seas come and go, this is all that remains. Millions upon millions of years of sediment compressed over time to form layers of rock, the building blocks of the canyon. But powerful forces were building deep underground, forces that would thrust these rocks a mile into the sky. We're on a journey to discover the geological processes that created the Grand Canyon. We are in the Cretaceous period, where plesiosaurs hunted in the shallow seas that covered the area near to where the Grand Canyon is now. Seas flooded and retreated over this area for millions of years, overlaying the ancient Vishnu Mountains with 2 miles of sedimentary rock. Half of that has since eroded away to leave today's canyon 1 mile deep. The next major transformation will push the land several thousand feet into the air. Deep beneath the earth, a monumental force builds up. It is one of the greatest forces on Earth, the gigantic power of colliding tectonic plates. Over millions of years, the planet's surface changes. Scientists explain the process using the theory of plate tectonics. The surface of the Earth is made up of a series of large plates. They float on the soft plastic part of the Earth's mantle. The inner core of the Earth may reach over 12,000 degrees. Heat escaping from the core creates convection currents in the next layer, the lower mantle, pushing the plates slowly across the surface. Scientists call it continental drift. Over time, whole plates move apart and crash back into each other, shaping and reshaping our world. Scientists believe that these colliding tectonic plates were instrumental in creating the Grand Canyon. Around 130 million years ago, the oceanic plate began to collide into the western edge of the North American plate. Oceanic plates are 30 to 60 miles thick and lie beneath the sea. They consist of dense basalt and get pushed down. Continental plates are mostly granite and lighter. Oceanic plates subduct underneath them when they collide. So when the oceanic plate hit the lighter North American plate, the oceanic plate moved under the west coast of America. Over tens of millions of years, the continental crust compressed and thickened. As the oceanic plate thrust downward, the whole of the west of America lifted slowly upward. As the land rose, the sea retreated, creating the landmass we see today. The collision dragged down portions of the leading edge of the continental crust. Beneath the surface, it melted, and liquid rock pushed up through the crust. The Rocky Mountains formed in the north. In the south, a range of ancient mountains, the Mogollon Highlands, grew higher. The area that today is the Colorado Plateau rose about 1 mile, lifting the ancient sea floor to where it is today, 7,000 feet above our present sea level. The region of the Grand Canyon was now high above sea level, but at this point, it was an unbroken plain. There was no canyon. Making the canyon took another force of nature, erosion. Even as the land rose up, a river flowed across the plain and began to cut down through the rock.
Here we have a colorful layer cake, which represents the rock formations on the Colorado Plateau and the Grand Canyon region, and the river itself is represented by this knife. Now, as the Colorado Plateau is uplifted, the river chisels its way down through and actually makes a cut, which is, whoa, I made a canyon.
70 million years ago, water and snowmelt flowed from the Mogollon Highlands onto the surface of the future Colorado Plateau. They began slowly cutting into the plateau area. Some of the old riverbeds are still visible, but they pose more questions than they answer. Richard Young, professor of geology at the State University of New York at Geneseo, has been trying to solve the riddle of the old riverbeds since he was a grad student. Young pieces together the history of rivers by looking at the shape and composition of rocks found on riverbeds. The modern Colorado River flows from the Rocky Mountains in the east to the Gulf of California in the southwest. But as Young investigated the ancient canyons, he found that something just didn't add up.
It was a shock for a student who just is getting started, and you want to believe what your professors are telling you, but everything you see out in the field says that something very different is happening.
To us, these look like big pebbles. To geologists, they're a missing link.
We see two things. We see how round they are, which indicates how far they've come, and secondly, the rock types are completely foreign to this area, and they come from at least 100 miles away from here.
The old stream pebbles are not native to the region where Young found them. They came from around 100 miles southwest of the plateau. The old river must have transported the pebbles from central Arizona north and west to the plateau region. The orientation of the pebbles in the riverbed shows the direction of the water flow.
Rivers cause pebbles to tumble in the river channels. They move until they reach this position with the current flowing this way. And that's a stable position, just like the shingles on a roof. And then that tells us that the river was flowing in that direction.
As the ancient pebbles settled on top of each other, they left a lasting record of how the river flowed. This was strong evidence that the rivers had to have flowed northeast, the opposite direction to today. But not only did the water flow in the opposite direction, it flowed in a different canyon, 4 miles south of western Grand Canyon. The old channel is now empty. What happened? Deep within the Earth's core, powerful forces were about to shatter the surface of what will become the Grand Canyon. About 20 million years ago, the oceanic plate began moving north relative to the North American plate. Heat built up onto the Mogollon Highlands southwest of the canyon. The Earth's crust began stretching. Over millions of years, vast areas of land deformed and cracked, sheared upward, or snapped down. The Mogollon Highlands fell thousands of feet. Huge basins appeared on low-lying land. Today, geologists call it the Basin and Range Province. Wayne Ranney uses dominoes to explain.
Once faulting begins, we tilt all the fault blocks down on individual faults, and you can see the surface tilting back into the Colorado Plateau edge.
Rock layers that were once horizontal are now almost vertical. The region tilted and then collapsed. Ancient history is written in the orientation of every outcrop. The collapse redrew the topography of the region. Before, the highlands to the south towered several thousand feet over the Colorado Plateau. After the collapse, the Basin and Range area was almost half a mile lower. It was a major piece in the scientific puzzle. The rivers may have changed direction because the whole landscape changed.
When the Basin and Range faulting occurred, it dropped that area. It made it actually lower than the Colorado Plateau. And that's the reason that the rivers were able to change direction and flow in the opposite directions toward California.
Scientists think they have solved the mystery of how the rivers reversed. But they were still 4 miles away from where the canyon is today. These ancient rivers did carve canyons, but not where today's canyon is, and on nothing like the same scale. Sometime after the collapse, a new river formed, the Colorado River, and it took a new course. But when and why? The challenge was to find the earliest sign of this river. Surprisingly, a clue came from outside the Grand Canyon. In the lower Colorado River, about 100 miles before the river enters the Gulf of California, scientists discovered a tiny fossil. Kristen McDougall, research geologist with the U.S. Geological Survey, has studied these fossils. They're called foraminifers.
Foraminifers are like specks of dust. It's a microscopic seashell. The Cretaceous planktic foraminifers that we find look like 3 golf balls hooked together.
Foraminifers are tiny. 100 of them could fit on a grain of salt. But they could show when the river began cutting the canyon. The foraminifers are not native in the lower Colorado River. Their home was much further north. The only way their fossil remains could have been deposited in sediments in the lower Colorado River is when the river transported them down.
They were originally deposited in Cretaceous shales on the Colorado Plateau north of the Grand Canyon. And they were eroded and brought down along the modern course of the Colorado River and redeposited.
Dating the sediments where the fossils were redeposited helps to solve the mystery. The sediments seem to have formed when the river took its present course, and geologically speaking, it happened just an eye blink ago.
These Cretaceous fossils indicate that the Colorado River became a through-flowing river by at least 4.5 million years ago. That's a very exciting find.
Evidence indicates that 4.5 million years ago, the river flowed along its present course from the northeast to the southwest. Scientists think they solved the mystery of the age of the river. But the solution raised a new question. They knew when the river had formed, but they were still not certain how. Evidence suggests that the river that cut the Grand Canyon began flowing 4.5 million years ago. In a blink of geological time, it cut a mile-deep slice through 2 billion years of our planet's history. But the subtle clues that led scientists to this knowledge raised new questions. Carving the canyon took a lot of water power. Slicing through a mile of rock is no small feat, even in around 4.5 million years. Where did the power come from? What natural processes provided enough water and enough power to gouge a mile-deep gash in the Earth's surface? The search for an answer has led to several controversial theories, and the scientific community still cannot agree. Most rivers begin energetically at their source. They rip through the terrain downward, eroding anything in their path. Downstream, things seem calmer. The water moves slower and the channel is wider. But back near the source, the river lengthens its channel upstream as the rushing waters erode more rock. They cut their channel headward. One theory is that the Colorado River got started this way. This headward erosion usually happens where the steepness of a riverbed rises. It gives the river more energy to cut deeper into the rocks. The steeper the gradient, the more rainwater channels into the river, and the faster it pulls down the slope. The river eats into soil and rock at the top and may also lengthen its channel headward. Could headward erosion have been the mechanism that made the Colorado River head out across the plateau? We know that the Colorado Plateau rose about a mile above sea level 70 million years ago, creating a steep slope toward the present-day Gulf of California. It's a neat explanation, but it's controversial. The modern Colorado River is only around 4.5 million years old, and the plateau rose 65.5 million years earlier. Perhaps there was another more recent uplift that would explain how the river crossed the plateau. Searching for clues, scientists discovered a layer of rock downstream in the lower part of the region called the Baus Formation. These rocks are around 6 million years old, and some parts are nearly 2,000 feet above sea level. When scientists took a closer look and discovered marine fossils in the rock, they knew they were onto something extraordinary.
There are 3 key fossils that we find in the Baus Formation. The first is a planktic foraminifer, which is one of the ones that floats on the surface of the water. And then there's a specimen called ammonia, and it's a very shallow water form. And then there's a third kind that lives much deeper in the ocean.
The fossils meant the rock layer is likely to have formed in seawater. For Dr. Ivo Lukita, the fossils led to a new theory of what had happened here. He believes that when the Gulf of California first opened up, it extended about 100 miles further north than it does today. Dead marine organisms sank to the seabed and became entombed in the white sedimentary deposit, the Baus Formation. Yet today, the fossils are hundreds of feet above sea level. That was the clue that he had been searching for.
One day, by looking at the present distribution and elevation of remnants of the Baus, it occurred to me that the Baus and the land with it had been uplifted as much as perhaps 1,700 feet in the last 5 million years.
He believes that this area was uplifted to its current elevation after the fossils were deposited, around 6 million years ago. And this second uplift created an ideal scenario for headward erosion.
By uplifting the plateau, you basically steepen the gradient of the rivers that emptied into the Gulf and therefore allow them to erode more rapidly.
The trouble is, not everyone agrees. The apparent existence of marine fossils in the Baus Formation, 1,000 feet above sea level, is not irrefutable evidence that the area was uplifted. Senior geologist John Spencer from the Arizona Geological Survey is not convinced about the second uplift theory.
I just was uneasy with the idea that the Earth would just go up and down like that. I call it trampoline tectonics. I didn't believe in trampoline tectonics.
Spencer and his team examined the Baus rocks in the lab. They are especially interested in the levels of strontium isotopes. Strontium isotopes found in these rocks are irregular atoms undetectable to conventional microscopes. They come in heavier and lighter forms. The relative concentration of heavy and light forms varies. It depends on the origin of the water. River water usually has a different strontium isotope concentration than ocean water. Depending on the concentration, scientists can often determine if sediment was formed in fresh water or in the sea. Spencer's graph of the isotope concentration of the Baus Formation confirms his suspicions. The green dots represent isotopic concentrations of seawater. The blue dots represent ratios typical for river water. The red dots are his readings from the Baus Formation. They indicate fresh water.
When we got our first results, it was immediately clear that we were seeing no marine signature in any of the Baus samples. We were a little surprised. We didn't expect that every number would come out looking like river water.
These results question the validity of the second, more recent uplift theory. If the Baus Formation was never under the sea, the uplift theory couldn't apply. and headward erosion along the lower Colorado could not have happened. Scientists had to look for another model explaining how the river cut across the plateau. About 250 miles west of Grand Canyon Village, there is a canyon system called the Lake Mannix Basin. Norman Meek, professor of geography at Cal State San Bernardino, believes this area may offer a clue of how its bigger cousin got started.
The Lake Mannix Basin has sometimes been called the Grand Canyon of the Mojave River because of the spectacular landscape that's portrayed here, a miniature version of the Grand Canyon.
The site of Lake Mannix Basin is connected to Silver Soda Lake via a canyon. Meek wondered if the formation of this canyon could throw light on the formation of the Grand Canyon. First, he examined the site of Lake Mannix. Lake Mannix is an extinct desert lake. It used to stretch over an area of more than 90 square miles. Yet many thousands of years ago, the lake disappeared. Meek wanted to find out when and why the lake drained. At the edge of Lake Mannix, he found sediments of ancient shorelines from the old lake. In the deposits, he found freshwater shells. He took them to a radiocarbon dating lab to find out their age. Radiocarbon is an isotope that occurs in all living creatures. Its half-life is almost 6,000 years, which means after around 6,000 years, half of the original amount is gone. By measuring how much radiocarbon is left in the shells, scientists can determine their age. Meek found that the shellfish in the Mannix Basin were alive 19,000 years ago, but after that, they died. At that point, Lake Mannix emptied. When he looked at Silver Soda Lake, he found that it existed from around the time when Lake Mannix emptied. Could these two lakes be connected? Meek suggested the canyon here was cut by a mechanism called spillover. He theorized that 19,000 years ago, heavy rainfall or snowmelts filled up the lake until finally the water spilled over the rim. The lake drained dramatically. Over a few thousand years, it cut down through the rock, carved a canyon, and then created Silver Soda Lake.
It's just like a reservoir breaking. There's a lot of energy. That energy rips away the sediments and the bedrock that make up the canyon, and you get a through-flowing river.
Scientists speculated that if spillover explained how a canyon formed in the Mojave Desert, it could also explain how the Grand Canyon formed just 250 miles to the east. Now, they just had to find the lake. Around 4.5 million years ago, a river began flowing across the Colorado Plateau, carving the Grand Canyon. Scientists are divided on how the river came into existence. They have two conflicting scenarios. The river either worked its way across the plateau from southwest to northeast by headward erosion, or the other way around by spillover. For scientists to apply the spillover theory to the Grand Canyon, they have to find a lake. And it is likely to be in the east where the elevation is higher. Today there is no lake, but there are 200 feet of green layered deposits, remnants of an ancient lake called Lake Bittahoche.
And so this green layer right here reflects the idea that Lake Bittahoche was in existence east of the Grand Canyon between 16 and 6 million years ago.
Over 10 million years, a lake deposited fine-grained sediments like silt, clay, and sand mixed with gray volcanic ash. The deposits indicate the existence of a lake, but they don't show how the lake overspilled and carved the canyon. John Douglas, geography professor at Paradise Valley Community College in Arizona, wanted an effective way to test the theory. He built a small-scale model of the Grand Canyon to demonstrate how the lake could have overflowed. 6 million years ago, the canyon wasn't yet carved, but Lake Bittahoche was full to the point of overflow.
And then as the lake came in, the lake filled. It filled and filled higher and higher and higher until eventually spilled across the lowest point across the Kaibab Plateau, and then water poured down the other side. Those waterfalls continue to retreat back, and the whole time you're cutting Grand Canyon.
Douglas suggests that Lake Bittahoche drained and formed a stream. The steep gradient of the riverbed caused the stream to cut deep into the rock. Over time, the size of the stream increased, and more water poured out of the lake, which in turn cut deeper and deeper into the rock. But not all geologists agree. They say there is no evidence of there ever being a lake large enough to carve the Grand Canyon. So at present, there is still no definitive answer as to how the river came into existence. What we do know is that when it began flowing around 4.5 million years ago, it cut a 1-mile deep scar in the surface.
To cut that whole canyon in 5 million years is a considerable feat.
Joel Pedersen, geomorphologist at Utah State University, is on a quest to discover how the river cut away the canyon walls.
The information that we collect from this, what we're doing is we're relating it to the history of the river. And so what the river is doing is, in the past, as it's eroding, it is also stopping sometimes and depositing sediment.
Pedersen is interested in finding out how fast the canyon erodes. He uses a technique called luminescence dating. This uses light to measure the age of a rock. It works on sediments containing minerals such as quartz or feldspar that have been buried in the dark. As sediments build up, it is gradually sealed away from the sun. Pedersen measures the amount of luminescence a sample gives off when exposed to light. This method can date sediments between a few hundred to several 100,000 years old.
We're collecting sediment that hasn't yet seen light, and the metal tube prevents it from seeing light. And we pull the tube out and take it back to the laboratory.
In the laboratory, scientists expose the samples of ancient river sediments to specific wavelengths of light. This energy excites the electrons in the sediments. Some respond by releasing their own energy in the form of light, and this minute signal is measured. The greater the response from the particles, the longer they spent buried.
So it's telling us that moment in time, how many years ago it was, that the river actually deposited that sediment and then buried it under more sediment so it couldn't see light anymore.
When Pedersen measured the incision rates along the whole length of the river, he found something unexpected. 179 miles downstream, the canyon appeared less deep. Something changed and lessened the river's cutting power. Could it be that the river lost its power due to changes beneath the land itself? It was an intriguing puzzle scientists were desperate to solve. 3.5 million years ago, the Colorado Plateau ruptured and created a deep chasm across the canyon. It's called the Toroweap Fault. Tectonic activity along the fault slowly lowered the land of the plateau to the west. And as the land fell away, it weakened the cutting power of the river flowing over it. Carl Karlstrom explains with a loaf of bread.
We'll imagine this loaf of bread as a stack of rocks that is going to be incised by the river to be the Grand Canyon. And we'll imagine this knife as the Colorado River itself, which over time can erode through even the hardest rocks to form a canyon. But many times there's a break in the crust called a fault. And so if I incise the river at the same time that I'm moving one block down, and I think you can see this if I turn it up like this, and you can see that on one side the canyon is quite deep and on the other much less deep.
Scientists had their answer. The river stayed the same, but the land west of the Toroweap Fault sank lower and so escaped the full cutting force of the water. The Colorado River has cut a masterpiece of a canyon, but water doesn't only destroy rock. Amazingly, it can also create it. Scientists are intrigued by new rocks within the canyon that are still growing. The Colorado River has been a great destroyer. In the last 4.5 million years, it has excavated over 800 cubic miles of rock. It created a gorge so big that all of the river water in the world would fill the canyon to just over a third. But the river can also create rocks. At certain points in the canyon, scientists have discovered new rocks forming today. Laura Crossie, professor at the University of New Mexico, is an expert on these rocks, the youngest in the canyon.
The big story of Grand Canyon is the carving of this beautiful place. There are other processes such as travertine that cause changes to occur and younger rocks to form inside that very canyon.
These travertines are special because they are created from water saturated with carbon dioxide, and they actually form at the bottom of the canyon itself. The carbon dioxide comes from deep inside the earth. It leaks out to the surface. Here, it dissolves in water, acidifying it and giving it the power to dissolve limestone. The carbon dioxide escapes from the water, forming bubbles like fizzy soda. As the gas escapes, it leaves behind calcium carbonate, which coats objects in its path. In some places, it forms stone waterfalls. In others, it covers sticks and twigs.
So these are just small examples of the coatings of travertine that form on every stick and twig and cobble that comes down the stream bed. It accumulates into vast piles of sediment which are instantly formed into rock, the youngest rocks in Grand Canyon.
Every drop in the river has in some way shaped the landscape here. But water does far more than destroying rocks and building them. Without the river, the current plant and animal life would struggle to survive. And it was the river which attracted early settlers here. When the ancestors of the Wallapai arrived in the Grand Canyon about 700 years ago, they celebrated the Colorado River as an important source for life, and it remains that today.
The river's all source of life out here. The canyon, to me personally, is something that our ancestors, they fought hard to retain because they knew the importance of it. Our wish is to maintain it in its natural state or its natural beauty.
Modern visitors of the canyon are mesmerized, as the first Native Americans would have been several hundred years ago. It's one of the natural wonders of the world. A monument to the age-old colossal forces that created it. $1.7 billion years ago, it began. Layers of flat-lying stratified sediments build up high canyon walls. Uplift elevates the plateau, and rivers cut deep into the rocks. And the climate today is arid. Nothing is lost. Everything is visible. It's difficult to find a canyon as impressive as this one. Possibly in southeastern Tibet, home of the biggest, longest, and deepest canyon, the Yarlung Tsangpo Great Canyon. The climate is different, and the area is covered with dense vegetation. The Euphrates is a very large river running through arid Iraq, a climate not dissimilar to Arizona. But this area never uplifted and formed a canyon. The Grand Canyon might not be the biggest and longest canyon on Earth. But the powerful forces that created it and made it unique are still hard at work. Nobody can predict how much uplift there will be. But if the river stays on course, then the future of the Grand Canyon looks good. And if you think this is grand, you ain't seen nothing yet. Stick around for another million years or two, and the canyon might be even deeper, with walls just as sheer as they are today. The Grand Canyon is just getting grander.